We had gotten quite a ways through example 7, but not through the whole thing. And in fact, there was one important step that we didn't get to find. I think Cassie had found that local max right before we left, but we probably didn't need it all written down. So we had all this good stuff that comes from first taking a look at your rational function, thinking about our objective, which basically at this point, our objective is do as much as you possibly can with any graph by hand. I mean, that's what we're after here. And that means we're going to factor whenever we can. That makes it easier to see those vertical asymptotes that come from the zeros of the denominator. And our horizontal asymptotes, we always think about what's going on with the degree. If we put infinity in here, what would happen? But we now know there's this interesting little sidebar called a slant asymptote. So if you don't get a horizontal asymptote, it doesn't mean that you are without information as far as asymptotes go, because you probably can divide and figure out a nice slant asymptote. And then our x-intercepts come from making y 0. And the only way to make y 0 is to make the numerator 0, because if there's a 0 on top of the fraction, then we're okay. And then our y-intercept, we just slap a 0 in here for x in all these positions and figure out what we would have left. And then once we get a little graph action on here, then we can go through and talk about the limits and all that good stuff. So where we were at yesterday was we had the limit notation filled out, and we had gone ahead and graphed this. But the issue was exactly where is that part of our objective that is going to be a local max. And we need that little local max piece. And we use the graphing calculator to get that because, again, we cannot find that by hand until calculus. Once you have calculus, then you're good. So this monster was, parentheses, 5x plus 21, because the calculator needs to know, take all of that and divide it by parentheses x squared plus 10x plus 25. And then we'll do zoom 6. Since our window up here is pretty much negative 10 to 10, we should be able to see what we need. And this one, unlike the other graphs that we've been doing, those hyperbolic branches just seem to go nice and smooth with the asymptotes, and this one has a problem. And we do encounter, and this had been asked about yesterday or the day before, is it ever going to cross those horizontal asymptotes? And the answer is yes. Horizontal asymptotes are nice. Usually they'll work for the branches if the branches are symmetric. These are not symmetric branches, so we're going to cross that asymptote, but we still find it and we still write it down when we can. So the next thing would be, I need to know how high up this graph goes. I need that information. It's one of our analyzing steps to our objective that's down below. So that's going to be second trace, and number 4, the maximum, and this is something we've done several times before. But you just want to make sure that Blinky gets on the downside of the hill and press enter, and then on the other side of the hill and enter through yes. And we're going to go to those 3 decimal places. So to indicate that with this one, we would put negative 3.400, and we've talked about that in the past too. If you're using a calculator, you need to get those decimals on there. So let's go all the way down here to local extrema for a second and put local max of our y value, negative 1.563, at x equals negative 3.400, because again, that shows those AP graders that you knew. I had to use a graphing calculator for this, and this is how we do the rounding with our graphing calculators. We go to those 3 decimal places. But important for our graph is that we make sure that it looks like we're going through that point. So at negative 3.4, we are at approximately 1.5, for our graph. And then vertical asymptotes, again, part of the objective, never cross them, never. Ever. Positive 1, oh, thank you. Put the negative in the wrong spot there, thank you. So positive 1.563 at x equals negative 3.4. Graphed it right. So now that we have that, let's fill in the rest of the good stuff that we have. Did you guys get it graphed before we left yesterday? The bell kind of caught us off guard. So everybody got the table feature, got all that on there. All right. So as we approach -5 from the left, positive infinity or negative infinity? Where's it going? Negative infinity. Boom, one down. Now come at -5 from the other direction. Come at it from the right. What are we going to put in for that limit? Negative infinity again, one down. So normally, that was kind of where we were going to stop, except now they also say analyze the graph. And to analyze the graph means more of our objective. We've got to do domain, range, continuity, all of that good stuff. So, domain. Did we have anything we had to leave out? Yeah, that was our vertical asymptote. So, negative infinity to -5, jump over it, and be back on your way to the right. Range. Take a look at this graph. We're going to use all the y values? We're not this time. So we have to think about what is that highest y value for that cutoff. Don't we already know that? What was it? Right there, 1.563. That's the highest point. So this graph is going from negative infinity, and it'll go up to that 1.563. Should we include that? Yes. Yes. Now, here's another one. Every once in a while, the book will use a parenthesis here instead of a closed dot. Here's their argument. It's not exactly 1.563, but we know that point was included on the graph. So we're going to go ahead and use a closed bracket there and say, yep, that is a point that's on our graph. So if you're looking at your homework and you're thinking, but I know this point is supposed to be here and the book does the parentheses, it's because their argument is we had to round to get that answer. So technically we're not going to include that one. But we know that that's a point, so we're going to go ahead and include it. Continuity. Continuous over all x. Finish it. Except -5. So without that asymptote, then we're continuous. Increasing and decreasing. Take a look at the graph. We have just one of them this time. Do we get some increasing and some decreasing? So we look at our graph, and we read our graphs for increasing or decreasing from left to right. And we start drawing this one, and well, that's definitely decreasing. But this portion of it is going to be increasing. So this time we're going to have both. We're going to have to label them. Yesterday we only had either increasing or decreasing, but this time we're going to have to do both. So increasing from where to where? From our asymptote to infinity? Yeah, this is where it gets weird, right? And that's because this one is so different. From here to here, it's increasing. But then it's going to pull back down and approach the asymptote. So this little piece right here is our increasing. So that's going to be from our -5 asymptote to, well, what was the x value for our max? What was it? -3.4, blah, 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 but we're going to put the 3 zeros on there, or 2 zeros, I should say. All right, so now we need the decreasing piece. A little easier, not as much messing around on the left-hand side anyway. So what do we put for the decreasing? Negative infinity to -5. So that's the first decreasing chunk. Now on the other side, we have to figure out what's the other one. And remember, a comma here or the word and, don't union that. Don't union that. So what do we put over there? what's the X value that we know that's gonna start us off? And how far do we go with that? Yep. I'm sure you're curious. The administrators are supposed to come through every once in a while for 4 minutes and just watch. That's what they're supposed to do. That's what Mr. Jordan is here for. I have been here for, since 1994. This is the first time he's been able to stay for the full 4 minutes. He also gets called away for stuff. So there it is. All right, symmetry. Is this a symmetric graph? Bounded means from above and below. Is this bounded? No. Oh, no, forever. Took care of our local extreme, our local max. This one have any others? Is it? Okay. So end behavior, overall end behavior. The limit as x approaches negative infinity. F of x equals. And the limit as x approaches positive infinity of f of x equals. This actually had me thinking this weekend, because if you had Mr. Peshman last year, I believe this was probably the first time you had seen limit notation was this year, because I don't think he taught that last year. So, is everybody feeling okay with limit behavior? Well, if we go to the left forever, where's this going? 0. Whoop. Infinity or 0? As we go to the left forever, it's supposed to approach that asymptote. So that's going to be 0. How about as we go to the right forever? It is 0, kind of in a weird way though. We're not used to it coming back around and doing that. It's like so. So the reason I brought that up was I want to make sure everybody gets limit notation. You know, that limit notation is going okay. Is there anybody that feels like I should explain a little more in depth? Because I assumed that everybody had had it before, but talking to you. Everybody's feeling okay about limit notation? All right. So, next up, this bugger. Boy, that look a little scary, huh? Woo! Well, easiest way to get across things here, you go after the factory first. That's the easiest way to see what's going on. So look at your numerator up there. Do we have anything that we could pull out of all of those? 4? Anything else? Let's do it. How about the bottom? Common monomial factor we could pull out? 3 and an x this time. Hopefully we can factor again, right? Let's. So it's not a perfect square trinomial up there, but do we have two numbers that multiply to 12 and add to negative 7? What are they? Again, not a perfect square trinomial down there, but do we have two numbers that multiply to negative 6 and add to 1? What are they? This is new. What do you notice about that that would be something new that we have going on? We definitely have a lot more zeros on the top and the bottom with this than we have ever had before. So, 12.
You took a 3 out of 36 is 12.
Thank you. Thank you.
Yeah, I was gonna see. Wait, what? Can we just list all for like an extra thing?
There we go.
No.
I said 12 too, I think. I think I said 12. What did I say? All right, so we've got that. New piece. This is going to cancel out. And remember, it's been a long time since you talked about that with your hyperbolas, but when it cancels, it is a whole. So what we would really like to know is, where would it be at? You know, where would we find this hole? Now, here's the problem. If we take a 3 and we put it in for x, up in here, it's not going to work. The reason it's not going to work is because it's a 0 of the denominator, and so it's going to make the denominator 0, and we'll go, well, we can't use that number, which we already know. So what you do if you want to know the coordinates for this point is you actually cancel this out and put it into your simplified form to figure out exactly where that hole would be at. So we would take the 3 and we'd plop it in here for x. And we just follow the order of operations. So on the top we'd have a -4. On the bottom our 3 plus 4 would be a 7. So we would have 3 times 3 times 7, which is 9 times 7, which is 63. At least we know where it is. It's obnoxious, but we know where it is. So -4/63. Now we've got a lot of stuff we can do. First of all, vertical asymptotes. Vertical asymptotes will be where? 0, -4. Do we have a vertical asymptote of 3? No, that's a hole. So x equals 0 and x equals -4. Those are our vertical asymptotes. But you know, it's not a bad idea to kind of write yourself a little note over here to remember that there is a hole at 3, -4/63. Because we kind of get carried away when we grab the graphing calculator. The graphing calculator doesn't know to put holes in our graphs. It doesn't have a clue. So we have to get that stuff on there. All right. Horizontal asymptotes, as if we hadn't done enough already, right? Think about your infinities. Because we're going to have infinity squared over infinity cubed. That'll reduce to 1 over infinity. Y equals 0. All right, x-intercepts. That's where we get y to be 0. And that's going to come from that. So where are the x-intercepts? 0. Except, what do we know about 3? It's a hole. So it's kind of like I said, you want to write this down here so that you remember, you know, every time I'm going to work with that 3, things get weird. All right, y-intercept means putting a 0 in for x. Some people are shaking their heads. Why are you shaking your head? It's an asymptote. Remember, it's a vertical asymptote. So here's another one where we go, wait a second, I thought that wasn't going to work. You know, so we can't do that. None? None.
Why is it?
Because remember, x equals 0 is our asymptote. So at no point are we going to be able to say, hey, let's put a 0 into this function because we'd be dividing by 0. So this is one, like I said, it's kind of step back. Okay, I know these things. Now I have to think about those things as I go through this graph. Alrighty. Well, we can write the limit notation. So we're going to approach -4 from the left and -4 from the right. Oh, was this f of x or did this have a different name? Still f of x? They did that in your homework a lot. They switched from f of x to h of x and k of x and all kinds of stuff. Get all the good stuff we know on there. Well, we've got our asymptotes at -4 and 0 for vertical asymptotes. And horizontal at 0. Let's see. X-intercept at 4, 0. At this point, grab a calculator, take a peek, and see what this graph has to offer. Parentheses for the numerator and the denominator. So let's get a few well-placed points. Since our asymptote was at -4, we probably want like a -5, -6 from our table. -5, -2.4. -6, -1.1. -7. And again, once you get a couple of them, you know what's going to happen. That's why we have that asymptote there. And when we graph it, we can see, yeah, the left-hand side is okay. It's going to work out just fine. Middle portion. -3, 3.11. -2, 2. -1, 2.22. So I want to concern with that point. I want to know, is that the lowest point? And that's also going to help me with my extremolator, so I might as well stop and find it right now. And that's going to be our minimum for the middle portion of this graph. .657 and 1.943. So not quite -2. And it should dip down just a little bit more. Right there. How much? A little bit. And then we'll go down here. And we'll pull min of 1.943 at x is approximately -1.657. All right, back to the graph.
You mean 9?
1.657, 1.943.
I heard you say 1.5.
Oh, okay.
Or
No, I've already moved twice today. I'd be watching for me too. All right, there we go. So now, concern. Remember this point right here? Is it possible that this graph maybe goes a little bit above the x-axis? It is, unfortunately. So if you want to zoom in on that portion, you could sure do that. It's just one of those things where we're going to get some points and we're going to do the best we can. But there's a lot going on here. All right, so we have 1, 8/10, 2, -2, blah, blah, blah. And what is up with 3? That's our whole. Yeah. So this is another spot where you catch yourself and you go, why does that say error? Isn't there supposed to be something there for that point? Well, remember, we said at 3, -4/63. So let's see what kind of number we're talking about for -4/63. There's going to be a hole. Right underneath. Right underneath. Put a hole. And there's our 4, 0. So it's hitting the x-axis, but then it's like it's bouncing back after a little while. Going above, just barely. And then it starts to go back down. So it is actually crossing, but we know what it's going to approach in the end, you know, and it'll go back down. So now we've got to fill in a lot of blanks. At -4, approach from the left. Where are we going? -infinity, we're going down. Approaching -4 from the positive direction, the right direction. Where's it going? Going to infinity. Approaching 0 from the left. Infinity. Approaching 0 from the right. Negative infinity. A lot going on with this one. Domain. We had some we had to leave out, didn't we? What did we leave out? Vertical asymptotes, where were those? -4 and 0, and we also had a hole, so we can't use that one. What was that one? 3. Well, for me, we're going to do our little jumper stuff. So -infinity up to our -4. -4 to 0. I'm going to need more space. 0 to 3. And 3 to infinity. And that's because, again, we have to leave out anything that gives us a hole, any kind of discontinuity, because we want to talk about the continuous behavior later. So, is 3 technically in the domain? Actually, we'd probably take it both ways, because if you put a 3 in there, you realize, hey, this is a hole in the graph. And you come back and you change it at that point and say, I can't use the 3. Range, we using everything with this one? Rats, right? There seems to be a spot there in the middle that we're not going to be able to use. So we have to figure out the highest point of these 2 branches. Should be over here somewhere, and we already found this one. So we're going to have to figure out that highest point now. We may have to do some zooming so that Blinky can actually figure that one out. So let's see, Blinky. I want you to hop down to that one first off. So I'm just going to hit right arrow. If you hit right arrow for a while, then Blinky will drop down to the next portion of the graph. And enter. Now, I have to go far enough so that Blinky is coming back down again. And I know it took a little while. So I'll try over there. And there it is. So, leave this up here for now. .057 for those coordinates for that highest point. So our range, negative infinity up to this, 0.057. And then skip over a little patch of y's and start up again at 1.943. Go up. So it's a nitpicky graph. There's a lot of stuff going on. Continuous. What do we have to leave out again? Over all x, but
Wouldn't the 0.057 be a local max?
it will. We'll write that when we get down there too. Exactly. Yeah, I didn't want to have to scroll because it's going kind of slow with the recording today. All right, so continuity. All x but, what are we leaving out again? -4. I'll just use a comma here. What's the other one that was a problem? That doggone hole. The 3.
So with the whole, you just leave it out of the exercise and then mention it in continuity.
Yeah, we have to. Increasing and decreasing. Whew. Well, maybe this part's easier. Decreasing. Decreasing with, oh, then it's increasing. And increasing. So this part's not easier. We've got more to do. So increasing first. All right, we are increasing from the bottom of our little U shape to 0. And the bottom of our little U shape was at negative 1.657. So let's see, we're increasing from there to our 0. Other increasing spot. Where's it start? 0, and it goes to 9.657, 0. Right, that's the point that we had up here. Right here. So this is increasing from 0 to this position, which is at 9.657 for the x. All right. Decreasing. Well, that one's a little bit easier for the first piece. Negative infinity to our -4. So that one's kind of nice. And then we have -4 down to the bottom there again, which would be -4 to -1.657.
But you did.
One more decreasing spot. Yeah. It says analyze. So where was the x cut off for our little local max up there? 9.657. We didn't, Cassie, I don't know that we gave you, I did the homework last night. I don't remember any as complicated as this one in example 9 from the homework. I don't remember any of them being like that. Sorry, I was talking about it and then I left it. 9.657 infinity. The homework typically doesn't ask you to do all of the stuff that we're doing. All right, is that nastiness symmetric? No. Bounded? No. Okay, so now that I've scrolled down here, I need that local max. local max of 0.057 at x equals, was that our 9.657? Yep. So we had our local min, we had our local max, end behavior. As we go to the left forever, what is our graph approaching? 0. As we go to the right forever, what's our graph approaching? 0. Now it's a lot like the last one. The last one had a little hill, but we could see the little hill last time. This is just a little tough to take out, and that's because of the location of the hole and all of the good stuff that we had in there. Did we fill every blank? Yes. Got them all filled. All right. Example 9. This is a doozy like example 8. So I'm going to stop right now and ask you to 43210 on how you're feeling about analyzing and finding all this good stuff we've been doing. As I've been doing your homework, I go through and I say to myself, this is stuff we've done before, but it's a lot of remembering that. So, do you think you could do, it's just thumbs up or thumbs down this, with a partner, do you think you could do example 9 on your own? Thumbs up or thumbs down? Okay, I'm not seeing the confidence I would like to see in order to get a candy partner. So, let's do this one together here. Make sure we got this all going right. All right, x cubed minus 16x over 2x squared plus 6x minus 8. Who doesn't that look like fun? And what do you notice? Take an x out. That ends up being a very good thing. How about on the bottom? We have a GCF we can take out there. Take the 2 out, make it easier to factor. All right, so x squared minus 16, pretty obviously, difference of 2 squares. X squared plus 3x minus 4. What are you going to factor that into? Plus 4 minus 1 adds to the positive 3. There we are. What do you think about right away, since it's one of the things that we encountered like 3 times during the other problem? What up there should give you pause right now? The hole. The hole, yeah. So write it down in a couple of spots so you don't forget, maybe even in a different color pen or pencil or something, you know, so you're thinking, hey, I've got a hole here at x equals negative 4. And I want to figure out where's that hole going to be. Well, to do that, we have to say, all right, if this cancels out, I'm going to be looking at x times the quantity x minus 4 over 2 times the quantity x minus 1. What would I get if I put it in there? So this would be negative 4 times negative 8 over 2 times negative 4 minus 1 would be negative 5. So we're going to get 32 over negative 10 and reduce it. You know, that's probably the best we can do. You know what? Maybe even better to put it in a decimal right now so that when you are doing your graphing later, well, negative 3.2, but that might help you out a little bit more. Do the negative 3.2. Can you see that? But now that needs to kind of stick in the back of your mind. Hey, I have a hole here, you know. So when we go down to talk about vertical asymptotes, like I said in the last one, I would write down that hole as well, just to make sure we remember that. So vertical asymptotes, where? That's it. Right. Whole. -4. -3.2. Horizontal. Oh. Come again, Ed? Oh, because there's no X out there, it doesn't matter. It doesn't matter. If there's an X, then there's an answer. But if there's no X, then we don't worry about it. Good question though. Alrighty, so horizontal asymptotes. No, but slant asymptote. We should do the division and get the slant asymptote. So where am I going to fit that? So we want that slant asymptote. And we look at this and think, okay, well, I've got a 2x squared out in front. What on earth am I going to multiply that by to get it to be x to the third? Does that have to be a fraction? It's going to be 1/2 x. And I'm not going to be able to fit this on here. So let me start over. 6x minus 8. Right, smaller or move it over. All right, so we multiply that by 1/2 x and see what happens. And that will give us, the 2 will be gone, x to the third, which is exactly what we wanted. And if it bugs you not to have the zeros up there for the squared and the x and all of that, you could certainly put that up there. But we need 1/2 of 6, which is 3, so 3x squared. And then 1/2 x, 1/2 of 8 is -4, and an x slapped behind it would be -4x. But don't forget to change the signs and add. And that'll mess up the next piece of it. All right. X cubes are gone, but now we have -3x squared, and -16x plus 4x is -12x. So we ask ourselves, can we go again? This is what we have. Can we multiply that by something to get a -3x squared? Yeah, it's -3/2. So this one has fractions for just about everything. -3/2. Because the 2's would drop out and we'll have -3x squared. -3/2 times 6. Give it as 6 over 1. Do a little cross reducing if you want to, or just think 1/2 of 6. So that would give us a -9x. And then -3/2 times -8, positive 12. Do not forget to change the signs and add, but let's put that -3/2 in there. So our -3x squared, x squared, that's gone. We'll have a -3x minus 12. Is there any way for us to multiply 2x squared by something to get -3x? Now we're done. We can't get a smaller x value out of this. So this is our remainder. And since it's -3x minus 12, we might want to change this to subtracting 3x plus 12 over this monster. But hopefully you're thinking, why are you going to all that trouble, Cedar Home? That's not the slant asymptote. The remainder doesn't get used for the slant asymptote. This doesn't. So there's our wonderful slant asymptote for this problem. So we need to find a spot for it. I'll put S-A, slant asymptote. And that one was our 1/2 x minus 3/2?
So I'm working on analysis instead of putting HA, we should just put SA and then put the sign.
You can do that. Yeah, just kind of cross it out. I do, when I was doing the analyze piece, I just put a little essay right here. I only put it in there. And there were no nasty slime passing hits like this, by the way. Nothing nasty like that.
X.
Like with
the last
X.
one.
All that stuff.
I believe we only have
2 minutes. We're not gonna get this done in 2 minutes, but let's see what we can do. X-intercept. When will y be 0? 0. Be careful. 0 and 4.
Negative.
Not -4. Why not -4? It's a hole. Yeah, that's that hole just messes up everything. All right, can we quickly put a 0 in for x and see what we would get? It's 0. Yeah, exactly. 0, 0. 0, 0. Well, I believe that last year I was gone and subtaught this and I didn't get far enough. And I think I have a video to finish up this example. So for those of you that really want to finish this one up, there's a lot going on here. I will put that video up for you. But I did your assignment last night, and it's not the toughest problems we're doing here. It's not. So it's the bottom one there. And I remember that even the toughest ones on this maybe took a max of 4 or 5 minutes because they weren't nasty. They didn't have the weird fraction thing going on. For most of them. There it is. We are detailed, that's for sure.
Mostly because
I'm not even answering the questions.